Okay, today we're in this demo we're going to learn a little bit about capacitance. So we learned in class that capacitance was defined by the charge you could put on something divided by the voltage that you hooked it up to. And so physically what that is let me turn it off for a second. These are two plates. Okay, they have an area of about 10 inches by 10 inches. And there are two of them, and I can slide them in and out at a fixed distance apart from each other. So what I've done is I've hooked one plate up to the negative terminal of my battery and the other plate up to the positive terminal of my battery. And when I flip the switch there, we can read off on the meter the capacitance of this parallel plate capacitor. So if you just take a look there, we've got a capacitance of 110 picofarads. Okay, so what do we have? Our capacitance is 110 picofarads. Now, if you don't remember what pico is, that's understandable. You're going to look on your formula sheet. The back side of the formula sheet reminds you what all the definitions of kilo, nano, pico are, etc. Okay, so 110 picofarads means 110 times 10 to the minus 12 farads. Okay, now my battery that I've hooked it up to is a 12-volt battery. Okay, so if I want, I can calculate now the charge Q that develops on each of these plates. The plate that's connected to the negative side of the battery will have a negative Q, and the plate that's connected to the positive side will have an equal Q, but it'll be positive. Okay. So Q equals CV equals 110 times 10 to the minus 12 farads times 12 volts there. So when I put that together, that's 1.3 times 10 to the minus 9 coulombs. Okay, and so that's pretty small. But let's figure out exactly how many electrons does that mean are gathered on the negative plate. Well, one electron is 1.6 times 10 to the minus 19 coulombs. So the unit of coulombs will cancel out and we'll be left with units of electrons. And so the answer there is 8.13 times 10 to the 9th electrons. Okay. So when I flip the switch, the first electron comes out of the negative side of the battery onto my plate. Nice and easy because there's no charge on it initially. And then the next electron tries to come through, feels a little bit of repulsion from that one single electron on the plate. But slowly, that many electrons, 8 times 10 to the 9 times 10 to the 9 electrons, gets built up on the negative side of the plate. Each time an electron goes onto the negative side of the plate, that forces one of the electrons that was on the positive side of the plate to exit the plate and flow through the red wire back to the positive terminal in the battery. So we get a current established initially, and then when we reach equilibrium, we've got Q on the negative side, negative Q on the negative side, and plus Q on the positive side. But once you get that Q there, it'll take some time to get those electrons to march across there. But with this little amount of charge, it does so pretty quickly. Now let's talk about the second half of that equation there. So we learned in the textbook that for a parallel plate capacitor, that the capacitance is epsilon naught A over D, where epsilon naught is the permittivity of free space. That was a constant. And it was related to K in the Coulomb's law. So K in Coulomb's law is 1 over 4 pi epsilon naught. Okay? But epsilon naught is just a constant. Okay? A is the plate's area. As I said, 10 by 10 inches on my particular plate today. B is the distance between the two plates. And like I said, this is not quite a half an inch, a little less than a half an inch. Okay? Now let's talk about what happens. These plates are movable, so I can change things about these plates, right? So what do you think will happen to the capacitance if I pull one of the plates outward so that only half of the plate, half of the area of the plates overlap. Think about that for a second. If I pull this front plate out so that only half of the area overlaps with the back plate, what will happen to the capacitance? Think about that at the microscopic level. What will happen to the electrons that are now gathered on the negative plate? Will they want to stay there? Will they want to move elsewhere? What do you think? Well, after you think about it for a sec, let's also look at our equations, right? It's good to think about something and get a feel for, your understanding of what will happen. But let's actually go to the equations, because the equations tell us the truth, right? So if we decrease A by a factor of 2, we drop A by a factor of 2, that means our capacitance goes down by a factor of 2, okay? So now think about why that is. Well, if I slide out the positive plate, right, the positive and negatives are attracted to each other. If I slide out the positive, they're not going to be so close to the negative charges anymore, and the negative charges are going to want to migrate back to the battery. So let's try that. Let's slide out one plate about halfway. Let's see, halfway is about there. And let's take a look at the meter again. Our capacitance has dropped now by a factor of 2. So now our capacitance is only about 55 picofarads. So when our A prime is half of the original A, then our new capacitance is 1/2 the original, 1/2 110 picofarads, or 55 picofarads. Okay? All right, so that's one example. Now, I'm using ratios, right, to understand what's happening here. So essentially what I'm saying is C, if all else is the same, meaning epsilon naught and D is the same, then C is proportional to A. So if I have A, I have C. Now, if you're not familiar with working with proportionalities, with ratios, let's actually remind ourselves what's going on. Why could I jump to that conclusion right away? Well, that equation is always valid. So for the new capacitance C prime, I could say C prime is epsilon naught A prime over D, right? D stays the same, so I'm not going to have D prime, it's just the original D. The old capacitance was epsilon naught A over D. So if I take this equation, and the top equation, and divide it by the bottom equation, C prime is C equals epsilon naught A prime over D, all over epsilon naught A over D. Well, epsilon naught's going to cancel, D is going to cancel, and I'll just get A prime over A. That's what it means when I say C is proportional to A. Okay? So if you're unfamiliar with working with ratios, it's okay to write these equations down twice, do the math, see what cancels, and once you've done this 10 or 12 times, you'll be able to look at the equation, write down the proportionality, and jump right to the answer. So this is a great technique for doing problems, especially if some of you are taking the MCAT exam. Doing problems on the MCAT exam, if you can do them by ratios really quickly, will get you a much better result on your MCAT exam. All right, let's do one more thing. So I said I could change the area there. So again, if I make the area go back, I'll go back up to that 110 picofarad. But this time, let's double the distance between our plates here. Get it right in the correct track. If I double the distance between the plates, now I've got a full inch rather than a half an inch. You predict what's going to happen to the capacitance. So when the new D prime, I keep the area the same, they'll all overlap. D prime is twice D. What happens to C? Well, D is in the denominator, right? So if I increase D by a factor of 2, then C has to go down by a factor of 2. So the new C will be 1/2 C prime. Again, if you want to do out the equations, you can do out the equations, cancel the things that stay the same, and you'll see that. So let's fire up the battery here, and sure enough, we're back to 55 picofarads when we're fully overlapped all A, but we've got twice the distance between them.